thanks to the Crafoord Foundation, to the Academy of Science for this organization of this symposium, and my congratulations to my esteemed colleagues for their outstanding works, opening new windows for the interior of stars. So my talk today will be mainly focused on physical processes inside massive stars. Ah, yes, I have to change this is this one. Oh, wonderful. Okay. As Hugues has mentioned, massive stars are cosmic engines that drives the evolution of galaxies. At the same time, they are very rare in one, let us say, stellar generation. We count about 3 stars more massive than 8 solar masses when 1,000 stars are born. So they are very seldom, but because they are very generous of their radiation, of their kinetic energy, of new chemical elements, they have a very strong impact on their surrounding. As Hugues has reminded, they go through the all nuclear burning phases up to the formation of a stellar core that will collapse. This is the end point of the nuclear lifetime. I must say that if we look at more massive objects, we can maybe make a little bit more, let us say, or find different families of massive stars. There are those which encounter an instabilities before forming an iron core. This instabilities is a Pair creation. It means that the photons are energetic enough for producing pairs of electrons and positrons, and this has a destabilizing effect that will make the core to collapse and sometimes to boost so much the energy production that the star will be completely destroyed. These are the Pair instability supernovae, which occurs between 150 and 250 solar masses, but it depends on mass loss rates, on the metallicity, and so on and so on. Now, after that range, there is, let us say, a largely unknown territory, but theoretically we can explore it. We can explore many things with theories. About between 150 and up to 100,000 solar masses, those stars will indeed become unstable at a given point of their evolution, but they are too massive for being destroyed, and probably they will produce supermassive black holes. Even more massive objects from, let us say, 100,000 solar masses up to 1 million solar masses, they will encounter, before the Pair instability, they will encounter a new instability, which is a general relativistic instability, which is due to the fact that these monsters are essentially supported by radiation pressure. And as you know, an object made of a relativistic particle is unstable. Those objects will collapse into a black hole. We don't know whether they exist, but as you know, we are observing supermassive black holes very early in the history of the universe. And maybe this is a channel through which such supermassive black holes could be formed. But my talk today, I would like to focus on physical processes, which can be important for single as well as for binary stars, I would say, or for triple also. So what are these physical processes? I have noted here 6 of them. Of course, there are many more. There is convection. I must say that convection remains one of the weak points in stellar modeling. As you know, convection decides the quantity of fuel for a nuclear burning. And what is complex in stellar modeling is to know the limits of the convective zones. And this remains a weak and unknown point. There are the instabilities in radiative zones, and it is where the physics of rotation, physics of magnetic fields can enter. Because normally in a radiative zones, if you displace a little blobs, it will come back to the equilibrium position. It's stable. If you want to make it stable, you have to tap somewhere the energy. I will come back to that point in a while. There are the nuclear reactions, which allow the stars to live so long lifetime. The neutrino emission that can be emitted and come to us directly from the central part of the star. So it's really it would be a wonderful sign of what happened in the central part of the stars. At the moment, we have only neutrinos from the sun, which is already a lot, I must say, and the neutrinos coming from the supernovae explosion of 87A. But otherwise, we have never observed neutrinos emitted during the advanced phase of massive star evolution. And this is normal because the present-day neutrino facilities cannot observe them. It would be extremely interesting to know whether Betelgeuse, for instance, is emitting a lot of neutrinos. We can say that if it would be typically at the end of carbon burning, the energy emitted under the form of neutrino would be 100,000 times more than the energy emitted under radiation. So it will be neutrino stars. The opacities and the equation of states are, of course, very important processes. Opacities can trigger pulsation. Equation of state for massive stars is relatively simple. It's perfect gas and radiation, except when there is percreation and when the central part becomes degenerate. But now I would like to touch three topics: convection, instabilities in radiative zone, and nuclear reactions. I will be very rapid here. Where in the stars and when during their evolution these three instabilities occurs. This is a very schematic, let us say, Kippenhahn diagram that I borrowed from a paper by Eni Lammers a long time ago. It showed the evolution of the total mass of the star, by the way, during the red supergiant star phase, which is the second panel here. No mass is lost, but it's not very correct, I would say. A lot of mass can be lost during the red supergiant phase. And the gray zone corresponds to the convective zones, the white, the radiative zones, and you have the H zone, which corresponds where the nuclear energy are produced and where the nuclear reactions are occurring. So we can see that convection occurs during the whole lifetime of a star. And it can occur at the surface during the red supergiant phase, in the core, of course, during the main sequence and the other helium burning phase, and also in intermediate region. Now, the instabilities in radiative envelope or in intermediate radiative zones will mainly have an impact during the first two phases of the evolution, because as we shall see, most of these instabilities takes long time. And so during the very advanced phase of the evolution, unless we are speaking of dynamical instabilities, they will have little impact. It's more what they produce as an impact during the hydrogen and helium burning phase, which is relevant for those instabilities in radiative zones. And the nuclear reaction mainly are hidden inside the star. But sometimes nature is friendly with us and the envelope is removed, either by stellar winds or by mass transfer in a closed binary. So how can we get insights onto convection, onto these instabilities in radiative zones, and to nuclear reaction that occurs inside the stars? Of course, there are many ways, and I have indicated some direct view. Typically, the neutrinos would be a direct view, but as I said, it's far beyond the present capacities. We can have those stars which are stripped, either because they are belonging to a multiple system or by stellar winds. Also, during the explosion, the layers can appear at the surface, or let us say, can be observed. Of course, they are mixed because they are not moving at the same velocities. And there are, of course, some more indirect view by looking at what happens at the surface of the stars, like the surface composition, surface magnetic fields, the pulsation, the oscillation, and also the surface rotation. This is for one stars at a time, but we can make some such observation for very large population of stars, and also to make some statistic about the way the Hesperus diagram is populated. I will come back to that point now. But let me touch now the first topic, convection. Actually, as you know, convection is very difficult to model in stars. Even in 3D, it's not so obvious. Actually, it involves many different space and time scales. And we have not the resolution to cover all the scales involved into this kind of processes. So the difficulties are huge. Nevertheless, some groups, like the group of Dave Arnett, but also in Raphael Hirschi in Kiel, are using multi-dimensional models to model convection in stars. And they choose to make this for advanced stage of the evolution, where the evolution is relatively rapid. And here what is shown are some models for the oxygen burning shell in a 23 solar mass stars. The above panel represent, or the colors represent the gradient in the oxygen, and the lower panel represent the density of kinetic energy inside these convective zones. What is interesting, we can see that the upper layers of this convective shell is increasing in mass. And you can see that the time scale is short. It's a few hundred seconds, you know. And this increase in the upper part is due, seeming, according to these authors, to some shear mixing occurring because the convective bubbles are turning around, of course, at the border of the convective zone, and this produces some turbulence. This makes the upper limit to increase in size. This is the process that is, for instance, not accounted for in 1D stellar models. Recently, in the group of Raphael Hirschi, they extracted from these 3D models some recipes to, let us say, to implement in 1D stellar evolution code. I must say that it will not be possible for long, at least from what I can see now, to make 3D stellar evolution, you know, because such computation requires months of computation for reproducing what happens in a few times 100 seconds. For modeling a star, you need millions of years for massive stars. You need millions of years, and you need, of course, to look for different initial mass, metallicities, maybe initial rotation. So 1D models would remain, in my view, still a very important tool for the future. So it's important to extract the information from these 3D models and to implement them in 1D model. And here, this is what has been done in this work by Laura Scott, where they accounted for the convective boundary mixing in 1D stellar evolution code. And they obtained that the end of the main sequence is given by this very heavy blue line that I have indicated here. The mass which are considered here are between 8 and 32 solar masses. And you can see that's very different from the shape of the end of the main sequence obtained by, let us say, step overshooting. The line on the left has been obtained with 0.1, and the line on the right, the most toward the lower effective temperature, has been obtained with 0.335. So you can see that it's very different. So who is right here? A way to do that is to look at how stars are distributed in the Hess-Pungusser diagram. And this has been done by the group of Sergio Simon Diaz in Canary Island with Castro and many others, where they have positioned the 600 OB-type stars in the Hess-Pungusser diagram by spectroscopy. And they obtained, indeed, this green line where the density of stars suddenly drops. And it drops because the lifetime of the evolution of stars beyond the main sequence is shorter. And so if we observe, let us say, a complete sample of stars, more or less complete, then we should observe a smaller density beyond the main sequence phase. And this is how this green line has been obtained. How these green lines compare with the convective boundary mixing that I showed before. You can see here. So it's not perfect by far, but it's better than the step overshooting. So it's just, let us say, a little progress that has been made here. But it shows a little bit how, in some fundamental aspect as the size of the convective core, we still need to make progress here. I am not a specialist of asteroseismology, but I feel obliged to show something about like this. And sorry if I am a little bit, I would say, imprecise. Actually, it's one of my students, in the postdoc in my group, Owen Farrell, who suggested a nonlinear inversion techniques. Actually, there are a description, detailed description in his papers. I will not go on that point particularly, but I want to show this because on the right you have period spacing of internal gravity mode, and you have 3 lines which are superposed, which are nearly identical, and these 3 lines correspond to 3 internal structure, and here by internal structure I mean the hydrogen profile inside different type of models. The red one corresponds to a 3.69 solar mass stars with a convective core at 0.58, and the mass fraction of hydrogen is about 0.35. It's middle of main sequence. The biggest convective core corresponds to the green line, which has a mass of 3.41, a convective core of 0.65, and these two models and the one in between, the blue line, are all given the same period spacing. So it's interesting to see the degeneracy, the possible degeneracy. Of course, here it's not a complete study, because it may be that other models would also produce such similar period spacing. What I can say here is that we have a difference of 8% of mass, of the actual mass of the stars, and a difference of about 12% in the size of the convective core. But despite of that, they give the same period spacing. Now I come to my favorite topics, the transport in radiative zones of stars. Actually, in order to include a transport into a 1D model, you have to follow a kind of roadmap. This roadmap first is to identify an instability, because you need an instability to make the things to be mixed in the radiative zones. In convection, you have convection, but in radiative zone, you need to think about something else. To some extent, it requires to know where you tap the energy, where you take the energy to allow the matter to go from below to above, let us say, to lift up the matter. Then you have to define a condition for this instability to be active. Maybe there is not enough energy. The energy that you can tap should be at least as big as the difference of potential energy required to lift up that matter. Finally, you have to study, in case the instability is working, how it transports energy, how it transports angular momentum, how it transports chemical species, and to find the appropriate equation. If I take the shear instability comes from the fact that when you have differentially rotating layers, it has actually a specific kinetic energy, let us say, that is larger than the average rotating layers, let us say. So we can say that the differentially rotating layer is an excited state that will decay to the average rotating layers. And so you can tap into this excess of energy to make the mixing. But in order to do that, you need to have that this excess energy is sufficiently large in order to explain the lift of the mass, which is called the Richardson criterion. Then you have to look at how long does it take for the instability to settle. In general, this is, for this case, for the secular shear instability, the Kelvin-Helmholtz time scale, more than a few times the Kelvin-Helmholtz time scale. So it's a long time scale. So long that the radiative diffusion can be operative, and it means that this kind of instability will not transport energy. But it will transport chemical species and angular momentum. And there are some numerical simulations by Vincent Prat, linear, that show that the efficiency for the transport of the chemical species and of the angular momentum is the same. And this is not so much accounted for in many different numerical simulations, where some factors have been introduced to make different the efficiency of transport of angular momentum and chemical species. Here, in that case, we finish with a diffusion equation with a diffusion coefficients. So, when we speak about rotating models, we are speaking about, let us say, models that include instabilities induced by rotation in the radiative layers. Actually, the convective zones are supposed to rotate as solid body in 1D model, which is maybe not true, but it is like this, that it's done in many models, in nearly all the models. In the different families of models that exist, I would say, in the literature, we can say that there are two families of models. There are the models which account for the hydrodynamic instabilities. These are based on the theory by Jean-Paul Zahn, who suppose that the two main instabilities are the meridional currents and the shear instabilities. These models predict some differential rotation during the main sequence, typically a core that is rotating 2-4 times more rapidly than the surface for typically 15-20 solar mass stars. And these models predict also that the main mechanism for the transport of angular momentum is meridional circulation, while the main mechanism for the transport of the chemical species is the shear, is a differential rotation. which scale with the gradient of omega, omega being the angular velocity. You have another family of models, which are the magnetic models, which are based mainly, at least this generation of models, on the paper by Engst-Spreut, and we call them the Taylor-Spreut instability, which have been, let us say, a different flavor has been proposed by Jim Fuller, and recently by Patrick Genberger, who is also working in Geneva, who has proposed a Taylor-Spreut calibrated theory. In those models, it's no longer the meridional current that transports angular momentum. The main driver for the angular momentum transport is the magnetic instability. And this is very efficient. This makes the star to rotate as solid body during the main sequence. It means that in those models, the shear mixing does not work anymore because there is no longer shear. And the mixing of the elements comes from the meridional currents, which scale the meridional currents as omega instead of the gradient of omega. I have indicated a few references where you can find models of these different types. Which one is the best? How nature is working? I would say there is more green light for the magnetic. Let us say, when we say magnetic instabilities, we should say magneto-hydrodynamic instabilities, because the hydrodynamic stabilities are also there, but it's magneto-hydrodynamic instabilities. I would say there are more green light for the magneto-hydrodynamic instabilities, because as you know, the sun is rotating over a great part of its radiative zone as a solid body. Also, the constraints from asteroseismology for the subgiant, for the red giants, indicates lower contrast than predicted by the hydrodynamic instabilities alone. On the other hand, beta Cephei stars, which are 9 solar mass stars, so already massive one, of course, slow rotators, some of them present clearly differential rotation. So, as always, everything occurs in nature, nearly everything. I don't know where I am now. It's finished? Oh, it's a pity. Okay. Okay, so I will not speak about that. but maybe just to finish, yes, maybe my point is to say when we are speaking about rotating models, it's not sufficient. You have to say we are considering rotating models with hydrodynamic instabilities or with magneto-hydrodynamic instabilities. Even if you say that, it's not enough, because it depends on how you include some instabilities numerically in the models. Typically, meridional currents very often are included as a diffusion mechanism. It's very different if you include the advector diffusive equation. This was my next topic. Thank you for your attention.
Thank you, Georges.